Hello everyone and welcome to a new lecture on discrete mathematics. So far we have studied different topics under the category of logic and proofs. We studied propositional logic and also applications that are envisioned for propositional logic. We learned about propositional equivalences and also predicates and quantifiers as well as nested quantifiers. In today's lecture I'm going to talk about rules of inference and introduction to proofs. In mathematics, we have something called proof, very important because without proof, we cannot claim statements in mathematics. Proof is officially defined as a valid argument which is used to establish the truth of mathematical statements. We need to prove it based on some facts, based on some arguments. Arguments here means we try to end up with a conclusion with a set of sequences. Sequences means statements, right? A sequence of statements, you can say. In proof, we talk about valid argument. What is the meaning of valid? It means the conclusion must follow from the truth of preceding statement of the argument. In other words, an argument is valid if and only if it is impossible for a statement to be true, only for this one, and the conclusion to be false, conclusion that we have drawn from these statements. In order to deduce new statements from statements that we have already, we need to use some rules of inference, and these rules of inference are building blocks or templates for constructing the valid arguments that we need. In fact, rules of inference are the basic and fundamental tools for establishing the truth statements. Let's see one example here, one simple example. We have two statements, statement number 1 and statement number 2. In the first statement, we claim that all men are mortal, right? All men are mortal. Everyone will die at the end. No one is going to be here forever. And we all know that Socrates is a man. It means, based on this statement, statement number 1 and statement number 2, we come to conclusion that Socrates is mortal. That's why we don't have Socrates anymore, right? He died, he was mortal because he was a man. He was a man. How, the question is, how do we get to the conclusion? How we come to this conclusion? Later, we will see. Let me give you one more example. If I have $1 billion, not $1 billion, 1 billion won, then I can buy a Lamborghini. If I have 1 billion won, I can buy a Lamborghini. Now, right now, I have 1 billion won. That's why I can buy a Lamborghini. Very easy, right? But later you will see not that much easy. So we can express the premises and conclusion in predicate logic as an argument. So we can say for all, you remember this one. For all men mortal, all men are mortal. Then Socrates was given to the function of men, right? Socrates as a man. Socrates was defined as a man, right? Then we conclude, this is conclusion here. So two statements, statement number 1 or premises, statement number 2. Based on two statements, we come to this conclusion that Socrates is mortal. As mentioned already, to construct valid arguments, we have to follow some rules. These rules can be inference rules under propositional logic, as you can see here, or we can go for predicate logic. In here, we have some rules. 8 main rules we have, namely called as modus ponens, hypothetical syllogism, disjunctive syllogism, addition, simplification, conjunction, and resolution. So we will study them one by one in this lecture. But before we go there, first let's see what is an argument and its accessories. Argument is a sequence of propositions that we come together to finally come with a conclusion. You know, in every talking, simple talking with your friends or your family members, you also do the same. For example, if you want to ask your father to buy something for you, first you explain some facts that, okay, I need this one for this one, if I have this one, then finally, okay, buy one PS5 for me, for example, or buy a car for me, buy a computer for me, or something like that. So based on some propositions, we come to a conclusion. An argument is a sequence of propositions, The final proposition are called as premises, and the last statement is called as conclusion. The argument is valid if the premises imply the conclusion. Finally, from premises we come to the conclusions. An argument form is an argument that is valid regardless of what propositions are substituted in the propositional variables. So from the definition of valid arguments, we see that the argument with premises of, for example, P1, P2, P3, and the conclusion Q, right? Then we can say P1 and P2 and Pn finally come to Q, and all this is considered as a tautology. So inference rules are all simple argument forms that will be used to construct more complex argument forms. The first rule that we are going to learn is modus ponens, or also called as implication elimination. This modus ponens is Latin word, and the meaning is the way that affirms by affirming. So the basis of the rule of inference modus ponens is this tautology: P and P implies Q implies Q. Using this tautology, we can come to this conclusion: P implies Q, P, then we can conclude Q. If P implies Q and we have P, then we can conclude Q because P already implies Q. Let's see one example. Suppose P is it's snowing and Q is I will study discrete math. So let's go for P and Q. This is P, this is Q. P implies Q is here. If it is snowing, then I will study discrete math, right? So this is P and this is Q. Now P happens, it's snowing. So based on these two facts, this is a conditional fact, this is a truth, right? Then we can conclude, so this is conclusion. These are the statements or premises. And this is conclusion. Therefore, I will study discrete math. Why? Because it's snowing. The next rule is modus tollens. Modus tollens. The corresponding tautology for this one is not P and P implies Q, then not P. What it means? If we say P implies Q, P implies Q, but now Q is violated by negation, then we can conclude not P. Simply saying, modus tollens says if a conditional statement is true and the hypothesis of this conditional statement is false, then the conclusion must be false. In this case, in modus ponens, we can say if a conditional statement and hypothesis both are true, then the conclusion is true. Let's see the example. P says, proposition P says it is snowing. Q says I will study discrete math. Okay, let's go for this one. P implies Q. If it is snowing, then I will study discrete math. This is this one. P implies Q. Not Q means I will not study discrete math. Based on these two facts, we can come to conclusion that it is not snowing. It means P also was violated, not satisfied, negation. So if not Q, then we can conclude this one. Why? Because this is a condition. The next rule is the hypothetical syllogism. A hypothetical syllogism is a valid argument for and a syllogism with a conditional statement for one or both of its premises. The tautology for this one is P implies Q and Q implies R. Then we can come to conclusion of P implies R. So let's see. Here we have three: P, Q, and R. It says if Q depends on R and R depends on Q, then we can come to conclusion that R depends on P. Let's see the example. It snows is P. Q means I will study discrete math. R is I will get A. If it's snow, then I will study discrete math. This one. This is P implies Q. This says Q, if I study discrete math, then I will get A, R, right? Therefore, if it is snow, I will get A. It means P implies R. The next rule is disjunctive syllogism. This rule is also known as modus tollendo ponens. It's a valid argument for which is a syllogism having a disjunctive statement for one of its premises. The corresponding tautology for this rule is not P and P or Q, then we can come to conclusion of Q. Here is it. P or Q, this is OR. P or Q, not P. We can say Q, right? Because it's OR. It's OR, it's not implication. It's OR. Or one side satisfied, it's okay. Example here, P and Q. Suppose P is I will study discrete math. Q means I will study English literature. I will study math, so this is P, or this is Q, right? These rules are very, very important in nowadays very advanced NLP and deep learning models. So maybe these are easy for you to understand, but for computer, when they want to do machine translation or online, real-time translation, it is very difficult to come conclusion. And for translation, understanding the concept or the context of the speech for computer is not easy. Maybe later in next courses, or maybe in advanced deep learning courses, you will learn about LSTM or recurrent neural networks or transformers. Then you will see that how difficult NLP is, natural language processing. So these are very helpful. P or Q. Then we say, I will not study discrete math. It means what? Negation of Q. And based on this rule, we can come to conclusion that I will study discrete math. Because one was violated, then we can go to second one. Addition is the fifth rule of inference that we are going to study for propositional logic. The corresponding tautology is P implies P or Q. It means P depends on itself or Q. Very easy, right? P, we can conclude P or Q. P depends on P or Q. So if we have P, I will study discrete math. Q, I will visit the Las Vegas. So P says, I will study discrete mathematics. There is no dependency between P and Q. Still Q can happen, right? So we can say, I will study or, right? When we come to or, then maybe both of them happen or maybe one of them happen, right? Sometimes we may have the statements and we try to figure out which rule is the basis of these statements. Sometimes we want to use the rules to come to conclusion, but some other time we have the example and we want to find the rule. Here is the example. It's below freezing no. One statement, right? It is P. And conclusion, therefore, is used for conclusion. It's either. Either means or. Below freezing, the same P, or raining Q, right? So we simply understand. We have one statement here, two statements here. So right now we did it. Addition, right? So we can come to conclusion that this is the addition rule. There are three more rules to learn for propositional logic: simplification, contradiction, and resolution. The sixth one is simplification. The corresponding tautology for simplification is P and Q, then Q, right? P and Q, then Q. Okay, we can come to conclusion to P and Q because P is already there, right? And when both happen, then it is N. Then we simply say that, okay, P already happened. Suppose our proposition is P, I will study discrete math. And Q says, I will study English literature. So I will study discrete math is P, and English, I will study English literature is Q, right? So we can conclude that, okay, this happened. Based on this, because this is and, so we can come to conclusion that this happened. Also, this also happened, right? This is called as simplification. Conjunction is the seventh rule, and the tautology for this one is PQ implies P and Q. I will study discrete math. I will study English literature. This is P and this is Q. So once we have I will study discrete math, this is a fact. This has happened already. That's why they are in parentheses. It means facts. This is different by P or Q, right? These are the facts. When this is a parentheses, it means happened, right? So this is one fact. I will study also one fact. So based on these two facts, fact 1 and fact 2, we can conclude that both of them happen, right? Both of them happen. The last rule of inference for propositional logic is resolution. Resolution plays an important role in artificial intelligence. We say that not P or R and P or Q implies QR. A little bit tricky, right? Because N is here, right? N is here. Not P or R, P or Q, right? So out of these two, R will come outside. It means not P or R, P or Q. We can come to conclusion QR, because R will come up here, right? R will come up anyway. Q also come up here, but P does not come up because this negation and P are in contradiction. That's why from these two we can conclude Q or R, not P or R, not P or Q, because P is in contradiction. So example P, I will study discrete math, or I will study English literature, and Q, I will study database. So not P means I will not study discrete math. In the second fact, we say I will study. These two are in contradiction, so we cannot come to conclusion. One time I said I will not study discrete math. In the second fact, I said I will study discrete math. So it's not a fact that can come to conclusion. So I will study English literature comes up, and I will study database. Then we can say I will study database or English literature, Q or R. So here is a list of rules that you can study And we will use these things for propositional logic and to build valid arguments. So far, we understood that the rules of inference which are applicable for propositional logics. So now we want to use a sequence of statements in order to make a valid argument. We can use those rules in order to construct valid arguments. If we have a single premise, then it is very easy. Maybe we need only one rule in order to make a valid argument. But it may not happen all the time. When we have many premises, then we must use several rules of inference to show that an argument is valid. In here, valid arguments are sequence of statements. Each statement is either a premise or follows from previous statement by rules of inference. Right? It means in order to come to some conclusion, maybe only one premise is not sufficient. As you can see here, maybe we use S1, S2, something, come to Sn, then finally we can come to this conclusion. Here is one example. We want to use a single proposition P and P implies Q to show that Q is a conclusion. Yes or no? Maybe finally we come that from this we can make Q as a conclusion or not. This is how we can do it. Here, steps, and here, explanation of each step. Number one, we start here, or you can say this is our fact. Based on this fact, we want to start and finally come to some conclusion, and we will see whether it's Q or not. If Q, then we say it's a valid argument. If not, not. So P. From this P and P implies Q, it seems using conjunction, we can do something. What is conjunction? Conjunction says P and Q, you remember I said these are independent, implies P and Q, right? This is conjunction. So from here, we can somehow conclude that P and P implies Q, we can think about P. Then, again, using the same conjunction from 1, we also can conclude P implies Q, right? We can come up with P implies Q. And using modus ponens, what was modus ponens? P and Q implies, P implies Q, P and P implies Q, all implies Q, right? And based on these 2 and 3 that we found here, we can say that, okay, Q can be concluded from this one, right? So here you can see P and P implies Q. P implies Q means P is okay, right? So then P is here, and then we can come to Q based on this MP. Translation example using propositional logic. So here we have some statements, and we want to try that based on these statements, we can come to a given conclusion or not. Again, I emphasize that in very advanced NLP, natural language processing techniques, such kind of rules are used. So these are our hypotheses. If it is not sunny this afternoon and it is colder than yesterday, this is number 1 hypothesis. We will go swimming only if it is sunny. This is the second fact. Third, if we do not go swimming, then we will take a canoe trip. Boat canoe, right? 4, if we take a canoe trip, then we will be home by sunset. And based on all, we will be home by sunset. Valid or not? In order to do that, we will translate it into propositional logic. First, if it is sunny this afternoon, we say this is P. Colder than yesterday, we consider it as Q. Taking canoe trip, yes, we will go swimming. Or sunny is what? Sunny is P. Not go to swimming is not R and S. Not canoe is not S. Home sunset is T. How do you translate this one? So first say not sunny this afternoon and colder than yesterday, Q. This is 1, right? So let me write here. Not P and Q. This is first one. Second one is we'll go swimming only if. It means only if, right? P. If and only if is this one. Only if is this one, right? We do not go swimming, not R, then S. We'll canoe trip. The last one is 4. So this is number 1, this is number 2, this is number 3, number 4. We will, if we take a canoe trip, it implies again, canoe trip, then we will be home by sunset, then it means T. Based on this, we want to see whether it happens, is T or not. So our hypothesis is, as we discussed already, and conclusion is T, right? How by this is, if we want to come to this conclusion. Okay, we start from 1, not P and Q. This is the starting point. Using simplification, do you remember simplification? Simplification says P and Q, you can just come up with P. So not P and Q, we simply go for not P based on these statements. R and P is this one, we'll come here, we start from this one. Based on MT, what was MT? MT says not Q and P implies Q, we can conclude to not P, right? Based on this rule, we can think about this one. R not R, P implies Q, then implies not P, right? So from here, we can think about R based on this one and these two. So not P here, then based on this fact, we can think about not R. Then here we have this one will come here as number 5, not R, then S. Using MP says P and P implies Q, right? Then based on 4 and 5 and also this MP, then we can come to S, right? Instead of Q, you think about S. And ST will come here. So we already have, based on this one, come to S, right? And we have S to T as a fact, right? Using MP, the same thing here, we can come to conclusion of T, right? Conclusion of T. S and S implies T, it means T. Just simply, instead of S, think about P, instead of S, think about P, instead of T, think about Q. And finally, you can come to T. This is how we can make a valid argument. In case of quantified statements, the valid arguments are a sequence of statements. In this case, each statement is either a premise or we make it using the previous statement. How we make it? Like what we did here. Exactly what we did here. We use some rules of inference and also rules of inference for propositional logic and also rules of inference for quantified statements that we can make it. So there are 4 main rules for quantified statements. We name them as universal instantiation, universal generalization, existential instantiation, and existential generalization. Okay, so we will study them one by one. One rule that is utilized for quantified statement is universal instantiation, or simply UI. We have a fact applicable for all x. If the fact is applicable for all x under some px, then we can come to conclusion of PC, universal instantiation, right? Universal means for all. In here, C is a particular member of the domain that this function is application, member of domain, right? So if it's applied for all, then for C also it is applicable. Well, C is in the same domain. Very simple example is here. Our domain in this example consists of all dogs. So we want to talk about all dogs. And Fido is name of a dog, right? So all dogs are godly. Based on this fact, when a rule applied to a set, all the elements will be affected, not only one or some or a part or 50% or 90%. When we say all, it means all of them we need to follow this rule. So when we say all dogs are godly, therefore Fido is godly as well. Universal generalization, or in simple UG, is the second rule that we use to handle quantified statements. This is used often implicitly in mathematics proofs as well. So UG is the rule of inference that states for all x px is true, for all x px is true if PC, this premise, is true for all elements of the domain. The element C that we select must be arbitrary and not specified. If it should be, it means this rule should be applicable to all. When we assert from for all x px the existence of element C other than it comes from the domain. This is very common in statistics when we want to use generalization. For example, I say all people in Guanjingo are living in villas, not apartments, right? Big apartments. So if someone comes to Guanjingo, maybe this Nongdong, maybe this part of Children's Park. If someone comes here and he sees a 20-floor store apartment, then it's not a valid argument. It means all these buildings should be maximum maybe 3 to 4 floors. The next rule to handle quantified statement is existential instantiation. We can use this rule to conclude that there is an element C in the domain for which PC is true if we know that there exists x px is true. If it is true, then for one element it's true. In this case, we should not select one value of C that we would like to have, but rather it should be a C for which PC is true, not for all like the previous one. Example says there is someone who got an A in this course. Let's call her and say that she got an A. For a specific, let's call her. A specific, not all. There exists means we can say, in the other words, say there is no one who got A, false. There is one who got A, true. All got A, false, right? This is the difference. And the last one is existential generalization, e.g., we use this rule to conclude that there exists x px is true, then a particular element C with PC is true, right? If we know one element C in the domain for which PC is true, then we know that there exists x px is true. Example is here. Michelle got an A in the class, therefore someone got A in the class, right? Existential generalization. From Michelle, we come to someone. Let's see an example to better understand what we discussed so far. Example is here. Using the rules of inference, construct a valid argument to show that John Smith has 2 legs. John Smith has 2 legs. This is conclusion from 1 and 2. show that we can construct a valid argument, this one, as a conclusion, based on every man has two legs, John Smith is a man, like the example of Socrates, right? So we say that mx is x is a man. So mx, x is a man in general. And lx, x has two legs. So mx says that x is a man, and lx says x has two legs. So here John Smith is a member. We say that it's an x. Right? So here we start. For all x, mx implies lx. What we have here, right? For all x as man implies it has two legs, right? Based on this, right? Then using ui, what was ui? ui was simply for all x px, we can conclude pc, right? Based on this. Then we say that mj something implies lj, right? Then mj, John Smith, for example, then we say using mp, right? mp was what that? P, and p implies q, then implies q, right? lj is correct. Why? Because here we say mj implies lj. And we come to mj as here, then we can conclude when mj implies lj, then lj is true as well. Example, use the rules of inference to construct a valid argument showing that the conclusion. This is conclusion. Someone who passed the first exam has not read the book. Someone who passed the first exam has not read the book. It means it is possible to pass the exam without reading the book. It is possible, not for everyone, for someone. How to come here? A student in this class has not read the book. Everyone in this class. So when we say everyone in the class passed the first exam, and also we say that someone did not read the book, it means there exists someone, not all, there exists someone who passed the exam without reading the book. How to prove this one? Okay, suppose cx is x is in this class. Bx means reading the book, and px means passing the exam. There exists cx, someone in class, and bx. Not bx means not didn't read the book. Bx means read the book, not bx means didn't read the book. So this is one. There exists someone in class who didn't read the book. For all cx, px, it means all students in the class passed the book, right? From this one, we can come to conclusion. First, what we did, we translate their statements and conclusion into simplic forms. Then in next slide, based on this one, we will translate. How we do it. Here is how to make a valid argument for this one. And this one is conclusion that we have. Okay, so we start from the first one. There exists cx and not bx, you remember, in class but not reading the book. So using ei, existential instances, we can come to conclusion that there is in class, and this is a is just an example, right? Just an example, and not a. Okay, a is in the domain of x. You remember that one. So ca and not. Using simplification, we have simplification like p and q, then p, right? Using this one, we can conclude about this. Then we had for all x, cx, px. It means all students in the class successfully passed the course. This is our premise, right? So using ui says for all x, px, then what? pc. Okay, ca, pa. It means a member, a is a member in the domain of x. If all passed, a also passed. Then we say this. Then from this one, we can come to pa. How? Using mp. mp says p and q, p implies q, all implies q, right? Then we can come to p. And if we simplified this one, simplification says what? Simplification says p and q, then p, right? So ca and not b, not a, this should be not b, right? B, not b of a. We can come to ba, right? Using this one. Then if we do conjunction for these two, conjunction says what? Conjunction says, you remember that one? P and q implies p and q, right? Using these two, we can say that pa, not b. That. Then using eg, in eg, existential generalization, we say pc for some element in C, we can conclude to there exists x, px, right? So from here, we can say that there exists px and not reading the book. So it means there exists someone in class who passed the exam without reading the. And this is and means both. We cannot say someone in the class passed the exam or not reading the book. No, both conditions. There is someone in the class who passed the exam without reading the book. Do you remember at the beginning of this lecture, we had the Socrates examples. All men are mortal, Socrates is immortal, then we concluded that Socrates is mortal. Now we want to make a valid argument. For all men x, non-x, mortal x, it means every man is mortal, right? Then using ui says for all x, px, we can come to conclusion of pc, where c is a member of x, not c. Man Socrates, we give to this function, right? Just c. This c, Socrates here is c. Socrates here is c. If c is in domain of x. Man, Socrates is a man and Socrates is mortal, right? Then we say Socrates is a man, then we come to using mp, p and p gives q, then implies q. We can say that Socrates is mortal. Here is a combination rule that is called as universal modus ponens. It's a combination of universal instantiation and modus ponens into one rule, right? So in here, A is a particular element in our domain, like previous example, element in the domain, right? This tells us that if for all Px implies Qx, if this is true, and if Pa, it means this function, whatever is applicable to A. Also, this is true for a particular element, for anyone that we want, and it should be in domain. Then we say that Q of A must be okay. It means if P is applicable for all, and Q also applicable for all, and P of A is correct because it implies, that's why we can conclude that QA is also complete. Okay, so in this part of the lecture, I'm going to talk about proofs and how to do proofs. Proofs are very important, not only in mathematics. Everywhere you need to prove what you claim. If you simply claim something without proof, people don't accept it. So in this section, we will study mathematical proofs, forms of theorems, direct proofs, indirect proofs using contrapositive and contradictions. A proof is formally defined as a valid argument that establishes the truth of the statements. In mathematics and computer science and also many other disciplines, even in simple life, informal proofs, which are generally shorter, are used. So there are some rules for using proofs that more than one rule of inference are often used in each step. A step may be skipped. Sometimes the rules of inference used are not explicitly stated, easier to understand and explain to people, but it's easier to introduce errors. There are many applications. For example, when you want to verify computer programs are correct, when you want to establish that operating systems are secure, where you want to enable programs to make inferences in artificial intelligence, showing that system specifications are consistent. And I simply say that whenever or wherever there is a claim, there must be a proof. So there are some definitions in this regard that we need to know before going for proofs and methods. The first one is theorem. A theorem is a statement that can be shown to be true using some definition, other theorems, axioms, rules of inference. The second definition is lemma. A lemma is a helping theorem that we use some already proved theorem to prove a new one, right? So we can say a helping theorem or a result which is needed to prove a new theorem, right? The next one is corollary, which is a result followed directly from a theorem. Then we have propositions. So these are less important theorems, are sometimes called as propositions. And conjectures is a statement that is being proposed to be true. You should remember that once a proof of a conjecture is found, it becomes a theorem. It may turn out to be false as well. So many theorems assert that property holds for elements in a domain, such as integers, real numbers, or some other discrete structure that we will study in this lecture. Often the universal quantifiers needed for a precise statement of a theorem is normally omitted by standard mathematical convention. For example, this is a statement that if x is greater than y, and if x and y are positive real numbers, then x2 greater than y2. Okay, so how we can prove this one? So this is a theorem, right? Later we will see. Many theorems have the form of for all x, px implies qx. To prove them, we show that C is an arbitrary element of the domain of x. So whatever domain of x is, then C is a member in this domain, right? C is a member of in this domain. Then we show that PC implies QC. So by universal generalization that we had in previous lecture, the truth of the original formula follows P implies Q. So we must prove something of the form of P implies Q. Trivial proof, if we know that Q is true, then P implies Q is true as well. For example, if it is raining, then 1 is equal to 1, right? If these are the facts, there are the facts. The other one is a vacuous proof. If we know P is false, then P implies Q. So if I'm both rich and poor, then 2 plus 2 is 5. If this is false, then both is true because we come up with a false, right? So it means the negation of all will be true, right? So the statement is the proposition, the proof is true, not the singular statements. Here we can see some basic rules for even and odd integers, right? So the integer n, if n is an integer, right? Even integer. So then there exists a k such that n equals to 2k, right? It means 2 multiply any k is what? Even, right? 2 multiply 3 is 6. 2 multiply 5 is 10, right? So 2 multiply any integer is even. The result is even. For odd, 2k plus 1, right? So this is odd. 2k plus 1, k, any integer, the result is odd. 2 multiplied 3 plus 1 is equal to what? 7. 2 multiplied 5 plus 1 is 11. We want to see proving the conditional statement of like P implies Q. We can use direct or indirect proof, right? Direct proof is normally used for more easier, right? So we can target this using direct proof. In direct proof, we assume that P is true. Then we use rules of inference, axiom, and logical equivalence to show that Q is also true for this one, right? This is for direct. For example, given a direct proof of theorem, if n is an odd integer, then n squared is odd, right? If n is odd integer, n squared is also odd. For example, 7 squared is 49. 5 squared is 25. So you can see that they are odd. Right? So we assume that n is odd. How we want to prove this one, right? We want to prove n is odd. Okay. Then we had that if it is odd, n equals to 2k plus 1, right? For k, whatever it is. Then we square this one. 2, right? So n squared equals to 2k plus 1 square. This one power 2, this one power 2, and 2 of this one multiply this one, right? Then if you simplify it, then you come with 2r plus 1. And 2r plus 1 is also odd, right? R or k or anything doesn't matter. This 4 is odd. So we prove that if n is odd, n squared is also odd. And this symbol is used when we successfully prove theorem, right? So they use this at the end. Here is the definition of rational numbers. The real number r is rational if there exists integer p and q should not be 0 such that p divided by q. So we learn in higher school that any rational number should be show it by p by q, where q is not equal to 0, right? Prove that the sum of two rational number is rational number. Okay, easy. R p by q is a rational number. This is a rational. Sorry. And also we consider this s is also rational. So we have 2 because it is sum, right? So we should go to sum of 2. So we go and we know that q and u both are not 0. This is the definition of rational number. Okay. Then there must be an integer p and q and also t and u. So we should go for this one. R plus s means sum of equal to p by q plus t by u. So we do, you know, from elementary school, qu, then this one pu, this one qt. Then finally we come with what? V divided by w. What is v? Pu and qt is v, right? And qu is w. Just anything, just assumption. So if we consider pu plus q2 is v and qu is w, then it is the definition of rational number. So simply we prove that sum of two rational number is again rational number. Very easy, and we proved it. So far we use direct proofs. Direct proofs lead from the premises of a theorem to conclusion. We started with by some facts, and finally we come up with a conclusion and we prove it, right? We started with premises and continue with sequence of deduction and end up with conclusion. However, there is a problem. Sometimes using proofs, direct proofs, we reach to dead end. We cannot do anything, right? Suppose we receive that, okay, we come up with something that odd number is 2k, so it is dead. So we also target the problem by indirect, right? Contraposition and contradiction. Assume not q and show that not p is true. This is our assumption, and this is what we want to prove. If we give a direct proof, of not q implies not p, then we have a proof of p and q. This is called as contraposition. This is sometimes also called as indirect proof, contraposition, or indirect. Let's see one example to understand contraposition. Suppose we want to prove that if n is an integer and 3n plus 2 is odd, then n is odd. Two facts are there. N is integer, 3n plus 2 is odd. Then prove this one. So contraposition. So this is what we want, right? So we go here and we assume opposite side. It said prove n is odd. We prove that n is even, right? So we start, then we go, and whenever we see, we will come back, right? So n is even. If n is even, then we have n equal to 2k, for k any integer what it is. Then we will put it in this one. This one will go to this one. 3n plus 2 is equal, instead of n we will put 2k. 2k plus 2, which is equal to 6k plus 2, right? And then if we take 2 out of here, then we will have 3k plus 1. So this one, from this one we will take, if we will take 2, this one divided by 2 will be 3k, and 2 by 2 will be 1, right? And if we consider this one just example j, then 3k plus 1 will be j, then we will have 2j for 3k plus 1. Therefore, because we come up with something odd, right? Opposite side. Then we say that it is opposite. Since we have shown that q implies not p, it means p implies q, right? Not we come from even, we come to this one. From the odd, we come to this one. If n is an integer and 3n plus 2 is odd, not even, then n is odd, not even. This is called as contraposition. Another example, prove that for an integer n, if n squared is odd, then n is odd. We use proof by contraposition to prove this one. We suppose n is even, opposite side, right? From opposite side, we start from not p. Not p is n is even here. So when we say n is even, in fact, we say it is not odd, right? Same. So if it is even, there exists an integer k, for example, where n is equal to 2k. So n squared, we put 2k squared, right? So n squared, it means 2k squared, which is 4k2, and if we take out this 2 outside, then it will be 2k squared. 2k squared is even, not odd, right? So we have shown that if n is even, n2 is even. Therefore, by contraposition for n, if it is odd, n2 is odd. Not p, not q, then p, q. This is called as contraposition. We also do proof by contradiction. This contradiction is used in many places. To prove p, we assume not p and leave a contradiction such that p not. In here, what we do, we start with the opposite side till we come up with dead end. Dead end means somewhere that we cannot do anything. So our assumption was wrong. When we say our assumption was wrong, it means what we are looking for that is correct. Indirect form of proof. So since we have shown that not p implies false is true, the contrapositivity implies p is also true. For example, the earth cannot be flat. Otherwise, we would find people falling off. So not. So because the earth is not flat, that no one fell down. Let's see one example. Use a proof by contradiction to give proof that root 2 is irrational. It means it is not rational. Okay. So we suppose that it is rational, not p, right? Opposite side. It says prove that it is irrational. By contradiction, based on this contradiction, we suppose it is rational. Then we will go to somewhere that it is dead end. And when we reach the dead end, it means our assumption was wrong. And when our assumption is wrong, it means this is okay. So when we say it like this, it means 2 can be written as a divided by b. And in this case, if we may do this one, then it means 2 equal to a squared divided by b squared. And it means, if you do just multiplication, it means 2b squared equals to a squared. Therefore, a must be even. a2 must be even. If a2 is even, then, based on the previous slides, if a2 is even, then a should also be even. Right? A should be even. And since a is even, we should write it as 2c or 2k, right? A should be written as 2k or 2c or anything, right? So, 2b2 equals to a2. 2b2 is equal to, instead of a, we write 2c2, right? Instead of a, we suppose here a is 2, 4c2. And then we come out that b2 equals to 2c2. Therefore, b2 should be what? Even, right? Because we could write it in this way. Again, b must also be even. So b itself should be even. But 2 must be divided both by a and b. This contradicts our assumption that a and b have no common factors. We say they should not have common factors. In b and a should not be divisible. They should not have. We should not divide it. It's a contradiction of our assumption that a and b have no common factor in rational should not. We have proved in this way that by contradiction that our initial assumption must be false, and that's why this is false and this is true. To prove a theorem that is biconditional means this one, right? That is a statement of this one, p, if and only p. We just need to show p implies q, q implies p. We already did it, right? So, for example, prove the theorem that if n is integer, then n is odd, if and only if n2 is odd. We have already shown in previous slide that p implies q and q implies p. So simply, we did it. If n is an integer, then n is odd, if and only if n2 is odd. So here is one question. We want to prove that 1 equals 2. And here we'll prove that 2 equals 1. How? Think about it and let me know what you come to conclusion about this. Where is the problem? Okay. I hope you understand the topic, and please feel free to ask me if you have any questions. Thank you.